Now we'll see x cube. So what is the capacity of x cube? We'll see. Can we use x cube as generator? Let's say your binary pattern is something 10010, whatever it is, and at output side or receiver side, let's say you got 00010. That means there is a single bit error, and we know what is the error term, right? Now we have to focus on only error term, correct? If you can divide error term, then that is not a good polynomial. So x power 0, x power 1, x square, x cube, x power 4. So this is the bit difference, right? So error polynomial is x power 4. Now x cube easily divides x power 4, right? That's why now syndrome will be 0. I don't know whether really there is an error or not. If there is no error, syndrome is 0. After error also, now this error is x power 4, then still your syndrome is giving 0, then we can't identify. That's why x cube cannot detect this kind of single bit errors. So how can you summarize it? Very simple. So x cube divides x power 4, x power 5, x cube, x power 6, everything, right? So that means, so whenever there is a single bit error at 4th position or 5th position, if you see, then definitely it can't detect. At 4th position also it can't detect. That's why 4th position, this represents 5th position, 6th, 7th, everything. So your polynomial x cube cannot detect any error which is occurring at 3 or 4 or 5 or 6 or anything. That means, so it is very weak polynomial. Easily we can understand, correct? Any single bit error it cannot detect if it occurs after 3rd position, or otherwise equal to, the 3rd position means, so here this is 0th position, 1st position, 2nd position, 3rd position. Then if error occurs at 3rd position also, it cannot detect. Understand? Let's see x plus 1 one more time. So this x plus 1 has one more problem. It cannot detect two single bit errors, otherwise double bit error, which is occurring contiguously. Example, see the situation 101101, and exactly 2-bit error is occurring and it is continuous like this. Hey, example here, if you get 100001, then this is the 2-bit error. Now what is the polynomial for the 2-bit error? That means e of x. Simple. This is 0, 1, 2, 3, 4, 5. We know that error will be x cube plus x squared, right? So whenever you have two errors like this, then that polynomial will have x plus 1 as factor. I can take x plus 1 factor. X plus 1 into x square. Just check it out. X square into x cube plus x square into 1 x square. That means what? So your error of x has a factor x plus 1, then x plus 1 divides it. Then again you can't detect. That's why, so x plus 1 cannot detect 2-bit errors which are occurring consecutively. If they are distributed, like one error at x power 7, one error at x power 20, that might get detected by your x plus 1. But if they are contiguous, like x power 20, x power 21, then error term will be x power 20 plus x power 21. Definitely I can factorize such a way that x plus 1 is one of the factor. So that's why x plus 1 cannot detect two single bit errors which are occurring consecutively, right? So that is the capacity of your x plus 1. Now we'll see some sophisticated polynomials. X plus 1 is not good, we have seen. Now x cube also not good. So any x power, some simple x power k is not good, right? X plus 1 also not so good, right? Then what are the good polynomials? We will see. So before going to that, first of all we will see some 2-bit errors. What is the structure of 2-bit error? If really 2-bit error occurs somewhere, but need not be contiguous, then what kind of error term you get, we will see. 101101, and let's see here 120 0110, exactly 2-bit error, okay? So also known as double bit error, double bit, then 1 becomes 0. See here, one difference here, one difference here. Then what is the error polynomial for this one? It's very easy. For that you should know the positions: x power 0, x power 1, x square, x cube, x power 4, x power 5. So it would be x power 5 plus x power 0, 1. So finally x power 5 plus 1 is the error. Then your polynomial should not divide it. If any polynomial does not divide x power 5 plus 1, then it can detect this error, right? Now let's generalize it. Any double bit error will have two terms. Sir, why here it is x power 5 plus 1? Because error at 5th position and 0th position, correct? 1 means x power 0. Similarly, if there are two errors, one is at, let's say, ith position, let's take this as jth position, and one error at ith position, then still this is a 2-bit error. Then what is the polynomial for that error polynomial? X power j plus x power I. Remember it. That means any 2-bit error can be represented as x power j plus x power I, where j comma I indicates the positions, right? So j is the jth position, I is the ith position, and my position start with 0. Remember, I am not numbering from 1, 2, 3, so on. I am numbering from 0. 0th position means first position. That means from right side to, if you go left side, then the first one is 0th position. So now you understand the structure of double bit error, right? X power j plus x power I. So here j is, notation is like this, j greater than I. Okay. Now I can do some simplification here. Since I is smaller number than j, then I can take x power I common. Then what you get? You get x power I into x power j minus I plus 1. So finally double bit error has an error polynomial such a way that it is nothing but x power I into x power j minus I plus 1. So you know the significance of I, correct? So this I is nothing but that is the starting position from right to left. If you go, see, from here to here while you are going, I is the first position where you got the error, then second error is at j. Okay. Now example, there is an error at 3rd position, there is an error at 20th position. Then what is the error polynomial for this one? So 0th position is there, first position, second position, 3 up to 20, right? Then according to this equation, it will be, the error polynomial will be x power I 3 into x power j minus I 20 minus 3 17 plus 1. So this is the way we can represent any error. Understand? Now if there is an error at 2nd position and 14th position, so very simple, x square into x power 14 minus 2 12 plus 1. In that way we can represent. So now we can easily analyze this error term and we can see the capabilities of all the error polynomials which can divide or which cannot divide these polynomials. We will see that. First, you remember at this moment, any 2-bit error can be written as x power I into x power j minus I plus 1. Okay. Now we'll see various polynomials and their properties, like whether 2-bit errors they can catch or not. Okay. So any 2-bit error can be represented like this, right? X power I into x power j minus I plus 1. So here, what is the value of I? What is the range of I? See, I is the first position where the, I can say from right to left, first error, right? So your error might occur, first error might occur here or here or here or here. Just try to find out what could be the ith position. I position can be here. Yes, first error can happen here. First error can happen here. In that way, the first error can happen here also. If there are n bits in your sequence, okay, then the range of I is from dash to dash. I can be 0, otherwise 1, 2, 3. So if there are n positions, the first position is 0, then last position is n minus 1. Then last I cannot be n minus 1 because there are two errors, right? This is the first error from right. Then obviously the first error can be at most here. So that's why I is from 0 to n minus 2. Now let's write this x power I into x power j minus I plus 1 into more simpler form. That is x power I into x power, let's take j minus I as t, another variable. So x power t plus 1. Finally, our 2-bit error is represented as x power I into x power t plus 1, where I ranges from 0 to n minus 2. Now the question, what kind of generator we have to take so that this polynomial cannot be divided? Remember always one thing, if polynomial gets divided, we can't identify the error. If so, that's why this is already error. So error should not be divided by our so-called polynomial, which is of course generator, right? Let's begin with x plus 1. Mr. x plus 1, are you good polynomial? It is not good polynomial, already we know that. If your error is x power 5 plus x power 4, that means x power 4, that means two consecutive errors. then we can write example at fourth position and fifth position, 5 and 4. Then it will be x power 4 into x plus 1, right? So any two consecutive 2-bit errors it cannot detect, already we have seen, that's why bad choice. Now we'll say x power 4 plus 1. This is also bad choice. Why? See, if we know that I value ranges from 0 to n minus 2, right? Then your 2-bit error might be like this, x power. So first position I value 0 and let's say j value something 4. If I take like this, then this error polynomial is nothing but x power 0 into x power t. What is t? J minus I. J is 4, I is 0. 4 minus 0, 4 plus 1. That means there is one error of this type. What is that? X power 4 plus 1. But if you take your polynomial as x power 4 plus 1, it divides it. Right? That's why, so x power 4 plus 1 cannot be good choice. Not only one particular error, see one more error. If I value is 3, okay, so j value is 7. Now try to write it. It will be, your error term will be x power I x cube into x power t. X power t is nothing but difference, 7 minus 3, 4 plus 1. Again you see there is a factor. That means whenever there are 2-bit errors, their difference is exactly 4, right? 3 to 7. That means the difference between the 2 bits is exactly 4 or 5, whatever. Then it can't, x power 4 plus 1 cannot identify it because it divides it. Now B is also not a proper choice. Now C is a good choice. I will tell you the reason. It is of course beyond our scope, but I will just give some idea why x power 15 plus x power 14 plus 1 is really good choice to detect this kind of any 2-bit errors. Now we'll see x power 15 plus x power 14 plus 1 and why it is a good polynomial. To understand that, first of all, we'll start with our error term. Whenever you have a 2-bit error, you get this kind of equation, x power I into x power t plus 1, we have seen already. And the range of I is 0 to n minus 2, where n is the number of bits in your frame. Now the question is, this x power I cannot be divisible by any polynomial if that polynomial has plus 1. Remember it. Example, you have a generator, it has plus 1, then definitely it can't divide x power I. I will tell you the reason. X power I is divisible by only two factors. One is 1, one is x, right? So if you want to write x power I, we should use only 1 and x, because only these two can divide x. Okay. Now example, let's say you have x square plus 1 that cannot divide x power I, because if they divide, then what happens? X square plus 1 into something, let's say some p of x equal to x power I, correct? Then my question is, x has only factors 1 and x, but you have x square plus 1. X square plus 1 cannot be a factor of x because the only factors are 1 comma x. Then this x square plus 1 should be should have again x as a factor, but x square plus 1 cannot have x as a factor, correct? So that's why remember one thing. So no polynomial which contains plus 1 which divides x power I. To divide x power I, the polynomial should be like this, x, otherwise x square, otherwise x cube. These are the only possibilities. If any polynomial contains plus 1 like this, automatically we can say that they can't divide x power I. Remember it. Now that's why we are happy. So your polynomial, any polynomial which you are going to take, if it has 1, then definitely it can't divide x power I. Now only thing we should take care is x power t plus 1. What if your polynomial divides x power t plus 1, then we can't detect the errors, correct? So this is the finally a form of double bit error, correct? Now, so the beautiful property of x power 15 plus x power 14 plus 1 is, x power 15 plus x power 14 plus 1 can divide only x power t plus 1 where t greater than or equal to 32,767, you remember. That means if t less than 32,767, then in this t, then such polynomial cannot be divisible by x power 15 plus x power 14 plus 1. So example, if your polynomial is x power 32,000 plus 1. Now question is it divisible by x power 15 plus x power 14 plus 1? No, that is what I said. We will see the reason for that. First of all, let's use this result. Now really at x power 32,767 plus 1. This polynomial actually is first polynomial I can say in the order which is divisible by your x power 15 plus x power 14 plus 1. So now we will focus on this number 32,767. The significance of that one, see what is t? J minus I, correct? That means j is nothing but one position where error occurring, and I is a position where one error is occurring, and they are from left to right. Now this is I, this is j. So j minus I is 32,767 means the two bits which are nothing but our errors are separated with 32,767 bits almost, right? One more or less doesn't matter. So they are separated by these many bits still, I mean up to that. Then if what I want to say is, if the error, we cannot catch the error only if the difference is more than this. See, if t value more than 32,767, then only we can't detect. But to have such kind of error, the error should be separated very long, right? 32,767. Example, any two bits which are having the error, their difference is 100 or 200, like up to 32,766 I can say. Even they are separated with 32,766 bits, then still your polynomial can detect it, because x power 32,766 plus 1 is your polynomial, let's say this one, then it is not divisible by this polynomial, right? So that's why we can detect it. So that is what I want to say. Finally, the importance of this number is, if they are very distantly separated, then only we cannot detect, otherwise almost, but it is very rare, right? See, why will you have two single bit errors especially, and they are separated with 32,767 bits? It is very rare possibility, correct? If and all you have single 2-bit errors, they will occur very frequently, like maybe in a 5-bit difference, otherwise 10-bit difference. Why they will have 32,767-bit difference, correct? It's very rare. That's why this polynomial can detect all the 2-bit errors which are quite common, like their difference is 100. That means they are occurring with 100 interval, 200 interval, 500, up to 32,767 interval. After that it cannot detect. Okay, so that's why this is very important polynomial we can use for CRC, cyclic redundancy check code. So we will see why it is having such property. That is what your question, right? Sir, how you got this magic number? I will tell you. So first of all, you should understand degree of a polynomial. Example, in this polynomial the maximum power of x is 15, right? That's why 15 is called degree, you know that. Now we will see what is order of the polynomial. Order of a polynomial, if let's say if it is p for any polynomial, that means it is going to divide x power p plus 1 where p is smallest integer. Okay, so any polynomial divides x power something plus 1 such a way that something is smallest integer among all such x power p plus 1, then we say p is the order of that polynomial. Example, let's say your polynomial, let's take one polynomial g of x. That g of x is dividing, let's say, x power 100 plus 1 and x power 200 plus 1, so x power 300 plus 1, so on. Then we say that 100 is the least number among all such x power k plus 1, right? Then this 100 is called degree of such polynomial. Remember it. So finally, you understand what is degree of a order of a polynomial. Okay. Now let's focus on primitive polynomial. So what is primitive polynomial? That's why it is advanced topic. If you don't understand also, not a problem, but I'm just giving the definitions. So we are not going into the details. No, don't worry. Primitive polynomial is a polynomial whose order is 2 to the power of degree minus 1. Such polynomial is called primitive polynomial. So actually this is primitive polynomial. So why it is primitive polynomial is out of the scope for us. Just remember, this x power 15 plus x power 14 plus 1 is called primitive polynomial. So for easy analysis, sir, how to understand this primitive polynomial, I will tell you. So this is like a prime number in our numbers. If you convert this to binary patterns like x value, if you take 2, then you understand you will get binary pattern 2 power 15 plus 2 power 14 plus 1. So this is the binary pattern of this x power 15 plus x power 14 plus 1. So 2 power 15 plus 2 power 14 plus 1 most likely will be prime number. Okay. So that means, so this polynomial is a prime number kind of thing in the polynomials. In numbers we have prime numbers. So here x power 15 plus x power 14 plus 1 is a primitive polynomial. So, but remember one thing, if you convert any primitive polynomial into binary sequence, that binary sequence may not be prime number always. Okay, remember it, just analogy. Now we will see this, since it is a primitive polynomial. What is the definition of primitive polynomial? Its order is 2 power degree minus 1. Let's compute order of that primitive polynomial. 2 power 15 minus 1. So 2 power 15 minus 1 is 32,767. Sir, what does it mean? That means any polynomial, recall the order of polynomial again. Any polynomial's order is something, then that polynomial is going to divide some x power e plus 1 first time at e value this order. That means, since this primitive polynomial's order is 32,767, so this polynomial is going to divide x power e plus 1 only if e value greater than or equal to 32,767, especially 32,767 is smallest e possible. Okay. So finally what I realized is this primitive polynomial can divide x power 32,767 plus 1. But before that, x power 32,766 plus 1 and so on, all these polynomials cannot be divisible with this x power 15 plus x power 14 plus 1. Now we'll come back to our thing. That means, so your x power t plus 1 also cannot be divisible by this x power 15 plus x power 14 plus 1 easily until this t less than or equal to 32,766. If at any time t value 32,767, definitely it will be divisible. Then you can't catch such error. But to have 32,767 as t, the difference between such two 2-bit errors should be 32,767. Understand? Or more than that. Then only your polynomial cannot detect. But that is very, very, very rare, isn't it? So that's why always I can say that occurs very rarely. Then almost any 2-bit errors can be caught by this x power 15 plus x power 14 plus 1. I am saying almost, not all, right? If the difference between the 2-bit errors is very long, like more than 32,767, then we can't catch. Otherwise, all the errors which are occurring in a closed interval, like with 100 distance or 200 distance or anything, can be caught by this polynomial. That is about this polynomial. Just remember it. Okay. So in GATE they don't ask questions related to this because it is very advanced thing, right? So to understand this results, then you should know what is order, what is degree, everything. Just remember it. If you understand, that's okay. If you cannot understand, simply leave it. Remember the result. This polynomial is good because it can, it can divide only x power t plus 1 if t is greater than or equal to 32,767. If you remember that, that is enough from this side. Okay. Now we'll see burst errors. We'll see how to design a polynomial so that burst errors can be caught easily. So let's say burst error is e of x. We will see what is the pattern of burst error first of all. This is your input. Now this is the starting point of burst and this is the ending point of burst. Okay. Now we know one thing, according to the burst error, definitely this bit, this bit is going to be corrupted, this bit is going to be corrupted, then only we say it is burst. But this intermediate bits may be corrupted, may not be, still we say it's a burst, correct? So this is a burst error structure. Now if you see error term, definitely since this is going to be corrected, then you get x power j in the error, e of x looks like this, right? Plus, so these remaining things can be anything, so I don't know exact structure, plus this last bit will be definitely present in the error term because that is also going to be corrupted. So this is the structure of burst error. It is quite similar to 2-bit error, correct? In 2-bit error you have only two terms, x power j plus x power I, but you have here x power j plus some other terms, but I don't know how many terms it has. It depends on how many bits gets corrupted. So at this moment let's take this as burst error. Now we have to study polynomials. such a way that, and we have to check whether what kind of polynomial divides this kind of error. That is not good polynomial. We have to use a polynomial which detects it. That means it should not divide it. Let's focus on that. So here again what we do is we see some math stuff, that means simplification. Since we know that I is smaller number, j is a bigger number in these two, then I less than or equal to j, correct? Strictly less than j I can say, because burst error contains at least two positions. So I less than j. Now we write like this. Let's take x power I common as it is. Then you get x power j minus I plus some extra remaining things, plus last one is x power, because you took x power I common, right? X power 0. So finally we got x power I into x power j minus I plus dash 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 plus x power 0. Now we have to analyze which generator or which polynomial is going to not divide this one. We will see that one by one. Now we'll see the analysis part. So this is your burst error, right? Now there are two components. One is x power I, second one x power j minus I plus so on x power 0, right? Now this x power I definitely cannot be divisible by our polynomial. Why? Because we have 1. Already I told you, whenever a polynomial contains 1, it can't divide x power I. Now our target become this part, right? Now let's see this one with various cases. So this polynomial in that j minus I, so if j minus I, we assume some variable L, okay? Now case number 1, what if this j minus I, which is nothing but L is less than R? Try to understand that. L less than R. We'll see this case number 1. Sir, what is R here? Our polynomial's degree, right? X power R. So whenever you have degree R polynomial, and now ignore this one, because however we are not dividing it. Our only target is this one. We have to prove that this polynomial cannot divide this one. That is what my wish. So I don't know whether it divides or not. So our wish is we should not divide this one. Now when j minus I is L, then this will become x power L. So that L less than R, that means what it will be with numbers. I will tell you. If R is 10, okay, then L less than R. Tell one number which is less than R. So definitely 9, correct? That means if this term, which is nothing but x power j minus I, which is nothing but I am assuming L, that L I am taking 9 plus something 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 plus 1. If you have this kind of burst error, okay, that means your burst error contains this component, then automatically we can detect it. Why, sir? See your polynomial. What is R value I am taking? R value 10. Then your polynomial is x power 10 plus something plus 1. So x power 10 plus something so on 1 cannot divide x power 9 plus something 1, right? You know the division formula. So definitely you are going to get some syndrome. That's why whenever this j minus I, which is L, which is less than R, where R is your degree of the polynomial, definitely we can catch this kind of errors. Now we'll see case number 2. In case number 2, L equal to R. That means that j minus I is exactly equal to your polynomial's degree. So for imagination, we'll take one example. Let's say your polynomial is x cube plus x square plus x plus 1. I also write binary representation for that. It is 1 1 1 1, let's say something, right? Okay, this is your polynomial. Now your error is, let's say, because L equal to R, right? That means x power j minus I is x power 3. So it is like this, x power 3. Let me randomly take x square, but I don't take x power 1, directly I will take 1. Okay, this is your error term. See, this is compulsory, right? Already I told you, whenever you have a burst error, first and last bit should be present, others are optional, correct? We know that. So now the question, this x cube plus x square plus x plus 1 divides this one? No, definitely it won't divide. It divides only if you have x, correct? That's quite obvious to see. Just try to divide it. So finally what I want to say is, whenever this degree of this error term j minus I, if that is exactly equal to R, still there is a very rare chance that your polynomial divides it. So example, if this error term is like x cube plus x square plus x plus 1, then sir both will become same, right? Yes, when both will become same, then only it divides. So now the question is, how many different error polynomials you might have generally? X cube is fixed, 1 is fixed. Let's write them. Okay, one is x square but not x. Second one, not x square but x. Third one, nothing, right? Fourth one, both x cube, x square and x. Out of them, only one is divisible by. That means if error contains x square and also x, then only it is divisible by polynomial. Let's see one more example. If you have polynomial x power 4 plus, let's say, only 1. This is your polynomial. Of course, we don't take this kind of polynomials because it has a problem. Already we have seen x4 plus x plus 1 we will see. This is your polynomial, divisor polynomial. So now your error is exactly like same condition, L equal to R. Then x power 4 plus 1 is compulsory, but the remaining things are optional. So random behavior, if I assume, let's say we have, let's say x cube but not x, not 1. Okay, so only x cube directly. Now the question, x4 plus x plus 1 divides x4 plus x cube plus 1. Definitely it won't divide, correct? Because they are having same degree. If you divide, x power 4 will be cancelled. You try it. X power 4 1 is x power 4. This will be cancelled, but this remaining remainder will be there and that cannot be divisible. Because the remaining terms you will get x cube plus something that cannot be divisible by x4 plus x plus 1. That's why now what I want to say is, now x4 plus x cube plus 1 is not divisible by this one. Not only this, x whatever you take here, if you take here x square, not divisible. If you take x cube plus x square, it is not divisible. So which one is divisible, sir? Only one pattern, that is x plus 1, right? If you have only this one, then only it will be divisible. Now finally I realize that whenever your polynomial's degree equal to that error's degree, I am talking about this area, this j minus I, then only in one possibility your polynomial is going to divide. That is the only problem we have. Otherwise every time we can detect the error, right? Now we'll see the probability of the detection. So what is the with what probability we can detect? Very simple. So for let's take r value 4. Okay, when r value 4, you tell me. So I can write, I write binary pattern so that it will be easy. Error can be written as binary pattern because that was the starting point. Did you remember? So your error is, let's say, x power 4, and in error definitely x power 4 should be there, 1 should be there, right? Now this is for x cube, this is for x square, this is for x, this is for your 1. Okay, so 1 bit should be present, x power 4 bit should be present, then only that is a burst error of this length. Now next, this is your optional, like so you can write 0 or 1, 0 or 1, 0 or 1. But question number 1, what pattern if I write, then that will be divisible by x4 plus x plus 1. I will write and you try to guess it. 0, 0, 1. Sir, why? Simply convert it into polynomial, x power 4 plus x plus 1. Exactly same polynomial like your generator polynomial. That's why it divides. Other than that, whatever the binary pattern you write here, randomly you write like this 1 0 1, then what happens? Your polynomial will become x4 plus x cube plus x plus 1. So it can't divide, it can't be divisible by x4 plus x plus 1. So now I have a formula to find out how many, what is the probability to detect the error. So to detect the error, to not to detect the error, what is the probability? We'll see. To not to detect the error, we have only one possibility. In these three positions, we have to write exactly like this one. x4, ignore it. So here, because you have x, definitely in the place of x, we have to write 1. And that's it. X cube 0, x square 0. Because x cube and x square are absent in generator polynomial, right? Now finally, sir, there is only one pattern which is, your polynomial is not going to detect, right? This is the only polynomial we divide. But how many polynomials we have? See, it depends on whether you write 0 or 1 here, 0 or 1 here, 0 or 1 here. Then 2 cube polynomials we can generate. Out of them, only one pattern is like this one. That's why with 1 by 8 probability we cannot detect the error, right? Now 1 minus 1 by 8 is nothing but 7 by 8. With 7 by 8 probability we can detect the error. Understand? Let's extend this to our R. When you have a polynomial of x power r like this plus something 1, Then how many bits you will have here? This is also same, right? This is your error polynomial. Error polynomial contains, I am writing here error polynomial, ex power r plus something 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 plus 1, right? Then let's imagine binary pattern for that. How many positions that binary pattern will have for that error polynomial? Definitely r plus 1 positions, isn't it? Now remember why it is x power r, because j minus I is r, that is the case. Now definitely to have 1 here, this bit should be 1. Definitely to have x power r, this position should be 1. Now only we have option for changing this. So sir, tell me one thing, how to have same pattern like this? Then whatever the pattern you have, based on that you copy here, correct? There is one pattern which is going to be a error. I mean, there is only one pattern which you cannot catch. Out of how many? First of all, how many patterns we can form here? There are r minus 1 remaining positions, isn't it? Total r plus 1. If I ignore this one and this one, because they are compulsorily 1, we can't change them. So remaining positions are r minus 1. Then how many binary patterns are possible? 2 power r minus 1. Out of them, this polynomial has one pattern, right? That pattern we should not fill. If you fill, then this pattern is going to divide it. That's why there is only one pattern we are going to divide. There are total 2 power r minus 1 patterns. That's why 1 by 2 power r minus 1 is the probability to not to detect the error. But to detect the error, we have 1 minus 1 by 2 power r minus 1 possibility. Correct? Or probability. So it's quite easy to understand. Just understand this one, that's it. So what is the probability to not to detect the error? To not to detect the error, then this polynomial, whatever you are using for generator, should be equal to this polynomial. To have equalness, we have to fill this pattern, but we can fill only one way. We can't have 2-3 ways, because see, x power r, same. 1 already same. But this pattern also should be like this one. There is only one way. Out of how many cases? But generally how many ways you can change r minus 1 positions? 2 power r minus 1. So 2 power r minus 1 are all possible cases. Out of one case should not arise. That's why 1 by 2 power r minus 1 is a probability to not to detect the error. Otherwise, this is a probability that your polynomial is equal to this polynomial. Remaining all the cases are nothing but definitely other than this case, right? So finally this is the answer. Now the third case is, what if your j minus I, which is nothing but almost length of the burst, which is greater than r is the degree of the polynomial. It is very difficult to prove, but the probability that we cannot detect the error is 1 by 2 power r for all that cases. Okay, so the result, just remember like a result, because it is very difficult to prove. So that's why what we do is we just remember the result. Whenever the burst length is greater, I mean not exactly burst length, but j minus I, let's take j minus I, that j minus I is greater than r, then definitely the probability that we cannot detect the error is 1 by 2 power r. So which is very rare. And let's summarize all the three cases. Case number 1, case number 2, case number 3. So this entire story depending on L comma your degree of the polynomial, where L is nothing but j minus I. Whenever you choose a polynomial of degree r, then that polynomial always detects errors in the case number 1. What is that? When that time, so L, which is nothing but j minus I is less than r. That means your polynomial's degree is greater than your j minus I. Definitely we can divide it. I mean, we can't divide that polynomial, which is nothing but this one. We can't divide it. So definitely we can detect the error. Remember. So that's why every burst error can be caught when j minus I less than r. If your burst error is little bit more than j minus I, such a way that if j minus I equal to r, that means this j minus I, this polynomial's power equal to r, then with 1 by 2 power r minus 1 probability we can't detect, but with remaining probability we can detect. That means this is very rare. When r is, example, your polynomial is x power 32 plus so on. Okay, this is your generator polynomial, r is 32, then 1 by 2 power 32 minus 1 is 1 by 2 power 31. So with this probability we can't detect. 1 by 2 power 31 is very less. It is 0.000000 something 1. That means it is very rare. With that probability we will not be able to detect that kind of error. So we are happy. Now if j minus I, which is greater than r, that means your burst length is more than your degree of the polynomial. That means maybe your j minus I value is something 60, 70, whatever it is, then the probability that we cannot detect the error is 1 by 2 power r. So almost same. Okay. So that's why again here also we have very rare probability that we can't detect it. So that is the story. Now let's choose one cyclic redundancy code, CRC polynomial, and we understand it. Example, your polynomial is x power 14 plus x power 15 plus 1. Okay, this is primitive polynomial, already I told you. Because of this one factor, this 1, so this is not going to divide this x power I. Now our target is this one. Okay, now we'll take one by one and each burst. Example, your burst length is, let's say I value is 10, j value 30. That means what? The burst length is 30 minus 10 by plus 1. That means 21. The burst error size is 21. So we know the formula for it, right? 30 minus 10 by 2. Then can we detect it or not using this one? We will see. So 21, right? So what is the formula? We have three cases: case 1, case 2, case 3. I minus j is what? 20, right? What is r? 15. So 15 versus 20. Since 20 greater than 15, right? This is your r. This is your j minus I. Since j minus I is bigger, then we can't detect all the errors, but with very rare probability we can't detect. What is the probability to not detect the error? 1 by 2 power r. What is r? 15. So 1 by 2 power 15 is nothing but 2 power 15 is nothing but 32,768. See, it's very small number. That means it is very rare to not to detect the error, right? So that is one thing. Second, what if you are having a burst length of something 10? That means j is 20, I is 10. That means you have a 10 bit burst error almost. That means 11 bit. So here what is the size of the burst? Length of the burst 20 minus 10 plus 1, 11. If you have a 11 bit burst, then whether we can detect or not we will see. First of all, what is r? 15. What is L or j minus I? J minus I is 10. Since this j minus I is less than 15, then it will become case number 1. In case number 1, always we can detect it because our polynomial is going to divide your error. It is not going to divide your error polynomial. That's why we can always detect. So that's why you remember these three cases. We proved case number 2 also, case number 1 also, but case number 3 was a little bit difficult, so you remember it. Okay, what is the probability that we can't detect here? 1 by 2 power r. So example of that case is this one. Let's say j equal to 20 and I value, let's say 5. Otherwise, let's take 4. Now see, what is the burst length? 20 minus 4, 16. 16 plus 1, 17. Whenever you have a burst length of 17, then see the cases now. R is 15, j minus I is 16, correct? Now your j minus I is greater than r, then case number 3, then definitely we can't detect some cases, but the probability of that occurrence of that case is 1 by 2 power 15, where r is 15, right? Again very rare. Understand? That's why don't worry about that kind of errors. Sir, but finally you are going to you are not going to detect the errors, right? Then how can we handle it? No problem. So whenever we can't detect the errors, still we send the error message, but we have other layers, right? Already I told you there is again one more layer that is higher layer. We are in data link layer. So very rarely we are missing some of the errors, it happens, but in the next level we have higher layer. That higher layer is going to detect one more time. So in that way we reduce the possibility. But remember one thing, nothing is 100% I can say correct in the world. So sometimes this kind of mistakes happens very rarely, then we should allow it. So no one can have perfect computer network. So definitely sometimes very rarely errors happens, but we have to avoid it. But if you can't avoid, then we should continue by that kind of errors. But of course we are proving that it is very rare, right? So that's okay. Understand?